Okay, thanks for this nice introduction. Okay, so let me first start with a very short recap of what we did yesterday. So we considered a dominant rational map of the projective space of dimension D. So it's defined by D plus 1 homogeneous polynomials without common factors, P naught, PD. And so we proved that the sequence of degrees, so they have the same degree, which is arguably the degree of f. And we proved that the sequence of degrees of the iterates of f is submultiplicative. So that by Fekette's lemma, the infimum of degree of fn to the power 1 over n is actually a limit. And in this dynamical degree, which is some number between 1 and plus infinity, sorry, excluded. Okay, and so recall also that I was very much interested in computing the growth of the number of periodic points per L. So per LF, for L some positive integer, is a set of isolated periodic points of period L. And the question was to describe how fast this, the cardinality of this set grows to infinity. So we computed, I did the case of automorphism of the affine plane. I discussed this at the end of the last lecture. And so remember that if f is an automorphism of the affine plane, then you have three possibilities up to conjugate by the right element of this group. Then you end up with an affine map. Lambda 1 is equal to 1. So I said de Jonquière. No, what did I say? I don't remember. Triangular, yeah, sure. Okay. Triangular. So remember x plus y, ax plus b, cy plus p of x. Again, lambda 1 is equal to 1. And then the interesting ones. Henon. Okay, so for it's the prominent example is x, y goes to y, and then ax plus p of y is the degree of p at least 2 and a non-zero. In that case, the lambda 1 is the degree of p. So it's bigger than 1. And it's an integer. So just to finish this discussion here, so you have a beautiful theorem by Bedford, Miley, Lyubich. Yeah, it's unordered authors. That says that, in fact, if you compute, I think we heard about Bézout theorem this morning. Did we have a proof? I don't remember for some reason. No, not yet. Okay, so if you apply Bézout theorem, you can show that this set grows. It's at most lambda 1 to the degree of f to the n. So here I didn't make any assumptions. So f automorphism of A2, and let me assume that f is actually Hénon. Okay, so of this form, or a composition of maps of this form. Okay, so what I said is that the number is bounded by some intersection of the intersection of two lines or two algebraic curves, and you can bound this by the degree of f to the n. Now the point is that you might have some some multiplicities, and a priori that might be very large. So the statement here is that, in fact, this multiplicity cannot be too large for too many periodic points. And so what they prove is that, in fact, this is equivalent to the degree of f to the L. So it's a highly non-trivial theorem, and it uses a lot of analytic and ergodic theoretic tools that I'm not going to explain. Okay, so the next example is easy example, endomorphism. Maybe I should have started with this, but of PD. So here you're assuming that the indeterminacy locus of F is empty. Okay, fine. So remember that we proved that a lemma, a little bit more general than this one, that said that in fact you have equality here between these two things, except if some hypersurface was contracted by Fm to the locus of indeterminacy of Fn. Okay, so here you don't have any indeterminacy locus, so the lemma applies, and so this implies immediately that the degree of Fn, in this case, is degree of F to the n for all n. Very easy. So lambda 1, again, is an integer. And then you have a similar theorem, which is due, okay, let me put a lot of names. So Fornes, Sibony, Briand-Duval. Let's say again, then you can compute the number. So here you're in dimension D, but already in dimension 2, the theorem is highly non-trivial. So you can compute using the analog of Bézout theorem dimension D, the number of periodic points of period L. You can prove that they're all isolated in this case. And you get an upper bound, which depends on the degree of F to the power L times D. Okay, fine. But then again, this problem of multiplicity arises, and their theorem says that, okay, most of the multiplicity are actually equal to 1. And so what they prove that the cardinality of pair L is again equivalent. So here you have the degree of F to the power D to the power L. Okay. So now I'd like to turn to more interesting, yet very elementary, but more interesting examples with respect to the problem of computing the dynamical degrees, or monomial maps. So what I'm going to talk about is a work by John Lilin that have been expanded by many people afterwards. Okay, so what is a monomial map? Okay, so you pick your favorite matrix with integral coefficient A, capital A of size D. Let me call the coefficient Aij. And then you look at the map. I'm going to call it F index A of W. So W is W1, WD is your favorite element in the multiplicative group of dimension D, or if you want, C star to D. And what you do is you take W to the power capital A. Okay, what does it mean? So you have many options, and I'm almost certain that what I'm going to write is not exactly the thing that I want. Maybe you have to change by transpose A, even though I try to check. So here you have, you look at W1 to the power A11, W2 to the power A21, WD AD1, and you continue like this. So W1 AD1. I'm going to give an example, okay? W2 AD2, etc. WD ADD. Okay, so let's do examples. Okay, so A 2111, A prime 1 minus 2 to 1. Okay, so there are two-dimensional examples. So here you should look at W1, W2 maps to W1 square, W2, W1, W2. And here is W1, W2 square, W1 minus 2, W2. Okay? Okay, so if I didn't screw up the action of GLNZ over of the multiplicative group, I have the nice following formula that if I look the nth iterate of the monomial map determined by the matrix A. In fact, this is a monomial map, okay? But attached to which matrix? Well, attached to the matrix A to the n. Okay. And so now the question is, how to compute the degree of Fa, and the degree of all its iterate, and the dynamical degree. So you see that, so we can make the exercise in the case of matrix A and matrix A prime. So to compute the degree, I have to homogenize this into P2. So in P2, let me take I should put a dashed arrow here. So the homogenization of Fa, what is it? So, okay, I don't have this in front of me, so it's Z1 square, Z2, Z1, Z2. So you have to have a homogeneous polynomials of degree 3, right? So here you put Z0, and here Z cube. Okay, so here this is, if you want, this is a monomial map also. Let me call it F A hat, where the matrix now is a 3 by 3 matrix, which is 3, 0, 0, 0, 2, 1, 1, 1, 1. Okay, that corresponds to the homogenization of this the matrix capital A before. So you can play the same game with A prime. Let's say F A prime. And so here it's a bit more subtle because you have some number, integer number, which is negative, right? So let me do this without thinking. So this Z1, Z2 square, and then Z1 minus 2, Z2. So you want to make this homogeneous, so you have to multiply by Z1 square. So here it's cube, Z1 square, and then you see that it's of degree 5, and so you have to put Z0 to the 3 and Z0 to the 4. Okay? No, it's not true? Here there is no Z0, Z0, Z0. No? What's the problem? I'm sorry. No? Okay. Bad students. Okay, so here you see the matrix A hat is 3, 2, 0, 0, 3, 2, 4, 0, 1. Okay, so the degree, so you do this same procedure. So I'm going to give a proof, a hand-waving proof. So when you homogenize Fa, in fact, it corresponds to F A hat for some matrix A J hat. Okay? So the degree of Fa, what is it? Well, this is the sum of all the column. Okay, the sum of the entries in one column, which is the same because each of these things are homogeneous of the same degree. So it's comparable to the maximum of the AJ hat. So let me explain here what I mean by this symbol like this. It means that there exists a constant which depends here only on the dimension, such that the ratio is bounded by C from above and by 1 over C from below. So you better have this maybe strictly larger than 1. Okay, so when something like this happens, then I write degree of Fa like this, okay? Just to simplify notation. Okay, and then this is an exercise that the maximum of the coefficient of your original matrix A are essentially the same as the maximum of the coefficient of the matrix F hat. And so let me cheat. Yeah. So the max is less or equal to the max of this one. and you have a converse inequality less or equal to D times the max of Aij. Okay, so I'll let you check this. So in other words, well, what is the degree of Fa? It's a complicated equation in terms of the entries of your matrix. Okay, maybe not if all the entries are non-negative, then it's fine. This is max of the sum of all the rows of your matrix. But if some entries are negative, then this is a crazy equation, which is a max of in for whatever. Okay, but at least what I know is that the degree of Fa is comparable to the max of the Aij. So now we are interested in the degree of the nth iterate. Okay, so this is the degree of f a to the n. And since this bound here is depends only on the dimension, does not depend on the choice of my matrix, this is a max of the norm of the entries here, Aij to the n, or the entries of the nth power of the matrix A. Okay, so what you recognize here is that if you take 1 over nth, the nth root of this number, this is comparable to the nth root of this number, okay, and the limit is going to be the spectral radius of your matrix A. That is the maximum modulus of all eigenvalues of your matrix A. So let me just write spec. So it's not the spectrum in algebraic geometry, but this is the set of all eigenvalues. And let me call rho of A. This is the maximum of the modulus of lambda for lambda in the spectrum. Then what I proved is that lambda 1 of Fa, well, proved, modulo the exercise, this is the limit of the degree of f n a as n tends to infinity. And so this is equal to, well, limit of this maximum, which is known to be equal to rho of A. Okay, so just to be sure, so here what I'm doing, I'm taking 1 over n of this, and so here I'm taking 1 over n here, and this 2 constant tends to 1. Okay, so which explains why the two limits are the same. Okay, so we're very happy. So consequence of this, lambda 1 of Fa, is no longer an integer. Okay, so if all the dynamical degree were integers, probably the theory would be much simpler and less interesting. But in this case, this is still an algebraic integer. So be careful, it's not an eigenvalue of A, it's the modulus of an eigenvalue of A. But still, so lambda, any eigenvalue of A is an algebraic integer. Then the modulus also is an algebraic integer of some degree. Okay. So I'll let you compute in the case of these two matrices. So you compute the eigenvalues. So here it's a matrix in SL to Z. So it has two eigenvalues which are quadratic, and one is larger than 1. The other one is its inverse. And here the two eigenvalues. So the discriminant of the quadratic polynomials determining the eigenvalues is negative. And so the two eigenvalues are complex conjugate in this second case. So you can compute them explicitly. Okay, so now I'd like to explain very briefly how you count periodic points. In this case, so A is a D matrix, and so it has D eigenvalue. So let me denote them by mu1 and I order them in the decreasing order for their modulus. Okay, so mu1 greater than mu2, etc., mu d. So if I want to look at so the set of periodic points, so let's say in the multiplicative torus, it's w to the power a to the l is equal to w. So if you want, the same as saying w a to the l minus identity is equal to 1. 1 here is 1, 1, 1, 1, 1. So you see that if you want to have isolated periodic points, this matrix has better be invertible. Okay, so I'm going to assume that no root of unity is an eigenvalue for A. And so under this condition, then per L of Fa is exactly the set of points, at least, okay, I'm not counting points and infinity, but here only in the multiplicative group, is exactly this set. So now how do you compute this? Well, you can check that this set is in fact included in the compact torus S1 to the D. And here what you're doing is that you're looking at the number of preimages of the point 1, 1, 1, 1, 1 in the compact torus. By the morphism, W goes to W A to the L minus 1, minus identity. And so in other words, the number of periodic points is, can be computed at a topological degree. And so you get an exact formula. It's the absolute value of the determinant of A to the L minus an entity. Okay, good. So let's say it's a corollary. No, yeah, okay, I have a nice formula, but now I'd like to have an estimate on how it grows when L tends to infinity. So you see that it depends on the value, on the absolute value of my of the eigenvalues. So let me suppose that the first k ones have absolute value greater than 1, and the other one less or equal. So then what you see is that if you look at the growth of this, so let me not be super precise because it depends on the whether or not your matrix is diagonalizable and so on. So I don't want to enter into too much detail. But at least when you take 1 over L's power of this, then it's going to converge to the product of the first k ones. Okay, so this direct consequence is purely linear algebra. And so as we shall see, when? On Thursday, yeah, so in 2 days, that in fact this number is actually lambda k. So I mentioned that dynamical degrees, there appears in any codimension, and it's going to be the kth dynamical degree of Fa. Okay. So this is, yeah, this is basically what I wanted to say about families of examples. Now, I'd like to state one result. And say the following. So, okay, so we take a dominant rational map from PD to itself, and then we start computing the degrees of the iterates. And I observe that if F is an endomorphism, so it doesn't have any point of determinacy, then the question is trivial. The degree of the iterate is powers of the nth power of the degree of F. Okay. So you have to realize that if you pick random polynomials, d plus 1 random polynomials like this, most of the time, in fact, they won't have any common factors. And in fact, the intermediate locus is going to be empty. So if you look, so the formal statement, I won't write it in the blackboard, but if you look at the collection of whole homogeneous polynomial, d plus 1 homogeneous polynomial of the same degree, then for their coefficient, so it's a projective space of the right dimension that didn't compute. But on a Zariski open-dense subset, in fact, it defines an andomorphism of PD. So the locus where the question of computing the degree of the iterates is interesting, in fact, very thin. Okay? So then I'm going to state a result that I read in a paper by Conta, Deserti, and Chi. And I don't remember, I think someone else had the proof of this, but you tell me, okay. Which is the following. It's a bit more general. That's what I explained before. Now you take any rational map which is dominant. Okay, so computing the degree of the iterates is very complicated in general. And then the claim is that you can compose or pre-compose or post-compose by an element in PGL D plus 1. Let's call it phi. And so the set of phi such that the degree of phi composed with f to the n is equal to the degree of f to the n for all n is a Zariski open dense in PGL D plus 1. So what it says is that it's a stronger version of what I explained before. It's that now you take any irrational dominant map. If you perturb it a little bit, so you post-compose by a generic element like this, then in fact, again, the question is completely trivial. So what it says is that, in fact, if all this problem of computing the degrees and so on is somehow analogous to the primary resolution of singularities in in algebraic geometry, right? If you give me a random equation, it's very likely that, in fact, the algebraic variety is going to be smooth, so there's nothing to say. But what you want to do is actually prove a resolution of singularities for any map, for any variety. Here it's about the same. So what we really would like to do is to understand the growth of degrees for any rational dominant map. Okay, so I don't know how much time I spent on this. Yeah, I can, yeah, well, okay. Let me give a very brief, yep. You prove this? What? Yeah, sure. Of f. It's not f to the n here. It's the degree to the n. Okay. Yeah. Yeah. Sure. Okay. If you want, it's like this. But in fact, this is the degree of you post-compose with an element or pre-compose the same. This is the degree of f to n. Yeah. No, but that's right. That you're always playing with n, and that they can move around, and then you say stupid things. No, I think this. Well, I don't know. I can remove your name if you want. No. No, I think you. Yeah. I don't remember, but I think it also appeared somewhere in maybe in a paper by Jeff. I don't know, or Bedford in some disguise. I don't remember. Anyway, it was proven in this paper. Okay, so the proof is as follows. So let me remember that you have the exceptional locus of f. So this is a set of all irreducible hypersurfaces in PT that are contracted by f. So what does it mean? It means that, remember, I defined the proper image of this. So if you look at the proper image of H, then, so the codimension of H is 1. So I want this to have codimension at least 2. Okay, so the first case is that if the exceptional locus of F is empty, then it's fine. Because by the lemma, in fact, for all phi in PGLD plus 1, the degree of phi composed with F to the n is equal to the degree of phi composed with F to the power n. Okay, so if you, to have problems to compute the degrees of the iterates, you need a hypersurface to be contracted to something smaller and eventually map after a zillion of iterates to the indeterminacy locus of F. So here what I'm saying that, okay, suppose that you don't contract hypersurfaces, then you can apply the lemma for any integers. Then exceptional locus of phi composed with F, the same of the exceptional locus of F, and so you get this for any phi. Okay. So what's happening in the case where the exceptional locus is non-empty? So let me assume, in fact, that this exceptional locus is irreducible, just to simplify. So let me assume exceptional locus of F is a singleton. And so I'm going to look, let me define UN. So it's going to be a subset of PGLD plus 1. So this is a set of phi such that what? Such that, let's say, the degree of phi composed with F to the j is the degree of F to the j for any j between 1 and n. So this is the same as saying this is a set of phi such that, okay, H is contracted to something of lower dimension, and you apply phi per phi n times, and until, so maybe at the n plus 1 iterate, you reach the indeterminacy of F, before you don't. So such that phi composed with F, j of H, is not included, I should say something like this, in the indeterminacy locus of F for all j from 1 to n. Okay? And so, in fact, by looking, for instance, at this, so when you look at phi composed with F to the j, this is algebraic condition in the coefficient of phi. And so having the equality like this says that UN is open, open Zariski inside PGLD plus 1. And so the key thing is to show that this is non-empty. If you show that it's non-empty, then it's dense. This is, now I understand why. Yeah, okay. You should have told me. Yeah, sorry. So, yeah. Okay, now I see the problem. So it's open Zariski dense, and in fact, my U is the intersection of all this UN. Okay, so, yeah, okay. It's a countable intersection, sorry. The heat, a countable intersection of Zariski open dense subsets. Yeah, sorry. Okay, so there is many ways to see why it's not empty. So one way is to do like this. So you have H here, and you have a problematic subset, which is the locus of indeterminacy of F. And so what I do is that I think I pick a point P, which is outside. Then by F, it's mapped somewhere. Then I can post-compose by phi, such that it comes back to P. And so in that case, what's going to happen is that phi composed with f of h, well, if you look at the point P inside H, its image, if you want, it's phi naught. So I choose phi naught such that phi naught composed with f of P is equal to P. And so this implies that this is not included inside the internal locus. Okay? And so your locus here is UN is non-empty for all n. Okay. So I've been took, yeah. Yeah, I know. That's true. So, yeah. So this is true also over, yeah. So the prime is true over Q, but if I say like this, it's empty, right? But they are also, okay, so I didn't check exactly what was the statement, but it's non-empty. Yeah, no, that's true. Yeah, but then the techniques are a bit different, and I don't want to get into it. It's just to emphasize the fact, why am I saying this? Okay, so Nessim is no longer here, but so Nessim Sibeni was my advisor, and I tried to promote to him the fact that it would be interesting to look at the degrees of the iterates for some very strange maps. And he's always, for many years, he was answered to me, well, for a generic map, the growth of degrees is trivial. So this is exactly what it says somehow, okay? So if you take something which is sufficiently generic, then the growth of degrees is exponential. But then, in fact, the theory behind dynamical degrees is extremely rich and interesting because you're looking at some, if you want, singular maps. They're very special maps where the dynamics on the indeterminacy locus or the exceptional component is very special. So the exceptional component like this or map for some contracted to some lower dimensional subvarieties and then back to the indeterminacy locus. So that's the main difficulty to avoid this kind of problems. Okay, I wanted to so before I go to birational surface map, and I use everything that Jérémy Blanc explained to us this morning, let me just state one general result on periodic points, because I'm not sure I'm going to come back to these problems later on. I'm going to focus the remaining of my time on dynamical degree. So I would like to state the following thing. So here I'm going to focus on in dimension 2. Okay, so rational, dominant. So remember that I defined lambda 1. Then I want to define lambda 2. So lambda 2 is the topological degree of F. So it is a fact that, in fact, there exists some open Dirac-Ski dense subset, a U and V, non-empty, such that F restricted to U is regular. But here it's even stronger, that F from U to V is in fact an unramified cover. And I'm going to, so it has a degree, and this degree is by definition this lambda 2. So in other words, if you pick a point P which is sufficiently general, so outside a closed curve, then you count the number of preimages on these things. It's always the same number that you get, and by definition, it is a topological degree. So for P, generic. Okay. So we're going to see this in greater generality, but the fact, topological degree is multiplicative. Okay, just apply this for A composed with itself. And also, you have this nice inequality that the square of lambda 1 is greater or equal to lambda 2. I just want to emphasize that this here, it's a consequence of Bézout theorem. Why is it so? So the picture is like this. Okay, so you take a point P, you want to count its preimages. So one way to do this is you interpret P as the intersection of two lines, L1 and L2. Okay? So L1 and L2 are generic lines cutting transversely at the point P. So now you look at its preimage. This is f minus 1 of L1. It's a curve of which degree? Well, of degree of f. And same thing for, f minus 1 of L2. It's also a curve of degree of f. And their intersections, there are two kinds of points. So degree of f minus 1 of L1, this is the same degree of f minus 1 of L2. This is degree of f. And if you look at the intersection points, you have two cases. So either this point is not a point of determinacy, and where can it be mapped? Well, it has to be mapped to P. But maybe sometimes it could be a point of determinacy, okay? So you remember that point of determinacy, it's mapped to a curve. And this curve could, cut L1 or L2 at some points. Okay, I can do this if you want. So if you have a point of determinacy, a blue point, then it's mapped like this. And so you see that when you're pulling back L1, since L1 cuts this point, it passes through the indeterminacy locus, and the same for L2. Okay, but by Bézout, the cardinality of f minus 1 of L1 intersected with f minus 1 of L2 is a product of the degrees, degree of f to the square. And what I said is that this is the cardinality of f minus 1 of P plus some extra stuff that comes from the indeterminacy locus. So plus some multiplicities that are non-negative, where P is in the indeterminacy loci. But anyway, so what you get these nice inequalities that the topological degree lambda 2 is less or equal to the degree of f to the square. Now you apply this to the nth iterate. You take 1 over n, and you conclude exactly this inequality. Okay? Okay. So now, last statement. So if you take a rational dominant map on P2, we don't have a neat statement as in for endomorphism or automorphism of A2 that counts the number of periodic points. You could have curves of fixed points, and then it's difficult a priori to estimate what's happening. But at least you have one general result. So f P2 to itself. So if you look at the number of periodic points of period L, you take 1 over L, this, and you take the lim sup, or lim sup, as L tends to infinity. Then this is less or equal to the maximum of lambda 1 and lambda 2. So here I want to emphasize that this is a very special case of a general theorem by Dean and Nguyen, which applies. So the theorem is not so difficult to prove in higher dimension when you're working on the projective space of dimension D. But it applies to any rational map on any projective surface, projective varieties, and even more. It applies also to scalar setting. So applies to meromorphic maps on compact scalar manifold. And what is interesting is that their proof is essentially analytic in the sense that it's analytic. It's not algebraic. It really uses current and some specific techniques that develop connected to the intersection of currents, and it is very subtle. So let me explain very briefly this statement, and then I turn to birational surface map in the, well, last 15 minutes, maybe not. We'll see. Okay, yeah, it's me. Always isolated, yeah, always isolated, okay? Otherwise, I'm not sure exactly what this means, so always isolated. Okay, so let me just explain. So again, afterwards, I won't come back to this counting of periodic points. But so the idea is, well, the general thing is as follows. So this is a square, okay. So here it's P2, here it's P2, yeah, I'm not a painter. So you consider the graph. This is what I mean by gamma. So this is a graph of f. So this x, f of x, x not indeterminate. Sure. And then I'm interested in, let's say, fixed points. So I want to understand what is the intersection with the diagonal. So it can be weird. So here, of course, it's not it's two-dimensional, and we are in 4 real dimension. But so you have nice intersection points here. Okay. So this point is smooth, transversal, and so on. So it's a nice point. But as we saw before, sometimes you can have intersection of things. It could be so that point could be a good point. So contribute to per L. But it could also project to point indeterminacy. And so you don't want to count them. And also you might even have like bad behavior in the sense that the graph could intersect the diagonal in, and have a positive dimensional intersection. So you could have a curve of fixed point. Okay. Okay, so the first thing that you do is that you want to compute the intersection number of gamma with delta. Yeah, so here what I'm going to do is just to simplify the discussion. So gamma is a curve in it's two-dimensional, sorry. Two complex dimensional. So its dimension is the dimension is 4 over the real. And what I'm going to do is I'm going to compute everything. So since I'm in P2 cross P2, which is a smooth manifold, I'm going to compute intersection number in Durham cohomology. I'm not going to explain this very neatly, but so first, gamma, the smooth manifold. So you can take its fundamental class in homology. Then you take the dual, the Poincare dual of this, and this is a class gamma, which is in the Durham cohomology of P2 cross P2, of which degree? Of degree 4. And the same for delta. So if you were like me here in 1998, which is unlikely, then you would have followed a course by de Mailly, which would have explained you also that if you have a smooth, or even not smooth, in fact, algebraic complex manifold, here in a projective case, you can look at this current of integration, and so you can look at its image in the at its class in dynamical homology, and this is exactly this class. Okay. So, yeah, probably I'm going to skip a little bit the this cohomological calculation. So here P2 cross P2, so you want to understand H4 of P2 cross P2. And here, so you know the cohomology of P2 of C. So it has only non-zero, one-dimensional components in even degree. And so here, in fact, it's generated by 3 elements. So here's real. So you have the fiber by the first projection, which I denote by point cross P2. Then you have the fiber of the horizontal projection. And then you have another element, which is determined by the product of a line with itself. So you pick a line P2 here, pick a line there, and take the product of them. Okay, and then you can compute. So I'm not going to do this, but you can compute gamma in this basis. And if I didn't screw up these things, so what you get is that you get lambda 2 of f times a vertical fiber plus 1 horizontal fiber plus the degree of f times L cross L. So how do you get this? Well, in fact, this all these things, you can intersect them. So for instance, the intersection of a vertical plane with itself, since you can move, is 0. Here it's the same. And the intersection with this and this guy is +1, and you can make all the computation. The intersection with this and this is 0, this and this and 0. So the intersection form here on this 3-dimensional space is, invertible, the perfect pairing. And so now to compute this number, you only need, so lambda 2, 1, and degree. You need to intersect the graph with the vertical with this and this one, and you get these numbers. Okay, it's an exercise. And now, so what is the intersection of gamma with delta? Okay. So so delta is in fact the graph of the identity, right? So you see that delta, it's here it's 1, and here it's 1, the sum of the three things. So when you cup gamma and delta, this is a number, and what you get is a sum of these 3 numbers. So lambda 2 of f plus degree of f plus 1. So we're going to be interested not only in the graph of f, but the graph of fl. And so here we get lambda 2 to the L plus a degree of fl plus 1. So you see that, so here you have lambda 2, but if you're able to relate this to the number of periodic points of period L, and you take 1 over L's power, then you're going to see lambda 1 appearing here. Okay, so now how do you relate this with pair L? So the claim here is that, yeah, okay, well, there is, so how do you explain? So I don't want to explain this. Okay, so so here what I'm going to do is, so there might be like a wrong intersection, so intersection of higher degree, of, a positive dimensional component for the intersection. So what I'm going to do is I'm going to perturb the diagonal a little bit. And if you perturb a little bit the diagonal, then in fact all the intersection, so I'm going to let gamma stay fixed, but then now the intersection are all going to be transversal. So how do you perturb this? Well, here you can use the fact that P2 is homogeneous, and so you can perturb delta, by pushing it by some generic element in PGL or 3 of C, let's say phi very close to the identity and generic. Okay, so this is something which is a general fact, is that the intersection here is the same as this intersection because the class of phi of delta, since you move by a continuous path, is the same. But now all the intersection, when you do this, when you perturb a little bit, all the intersection have become transversal and zero-dimensional. So what's happening here is that, okay, there are these points in per L that stay close. So when you have an intersection of which is proper like this, then maybe when you move, you have more points, but then the number of points is, so maybe it explodes into finitely many points, but you still have a positive number here. And what's happening here, so before, remember that the intersection was a curve, and when you perturb a little bit, now what you have is that you have a contribution which is a finite number of points which is non-negative. Okay, so I'm really hand-waving here, but what you're saying is that in fact this intersection decomposes at the sum of per L. So maybe let me be more precise, as the sum of some multiplicities, nu x for x in per L, nu x non-negative, plus a sum of other multiplicities, let me call it nu c, for c curve such that FL restricted to C is the identity. And this argument of perturbation, which was very vague, I must admit, says that also these multiplicities are non-negative. So all in all, what you conclude is that the number of isolated periodic points of period L is bounded by 1 plus lambda 2 to the L plus degree of f to the L. And so if you take the 1 over Lth power of this, and you take lim sup, that you get exactly the statement that I put down on the blackboard upstairs. Okay, so 3 minutes. So the comment is that the same computation works perfectly in PD, except that now you don't have the max of lambda 1 and lambda 2, but you have other dynamical degrees. So this proof is work exactly the same way. Now the key inside is that by Dean and Nguyen is that in fact you can work over any projective manifold, and then the proof is much more difficult. Okay, maybe I'm going to finish by writing down some references on this problem on computing on periodic points in general. So I said that there is this paper by Dean and Nguyen. So in the case of birational maps, birational surface maps, there is a paper by Iwasaki and Uehara, where they try to make this more precise, okay? So here, you're very close, in fact, to have a very precise formula. If you're able to show that, as I said before, that maybe most of the nu x are equal to 1, and maybe you can bound this number, then in fact, you have an exact formula up to bounded terms. So this is what they do in their paper. And then there is a very nice result, which is not about counting, but about the Zariski density of periodic points by Genie in any dimension. But it's his first paper was exactly in this case under the assumption that lambda 1 is different from lambda 2. So he proved that, okay, I think in the paper it's proved for birational map, but the argument works for any rational map for which lambda 1 is different from lambda 2. And so he proved that the set of isolated periodic points of period L is Zariski dense. So which is some kind of a transversal information to this counting thing. Okay? So Thursday, birational surface map and the general case. So I have 2 hours and 30 minutes. I'm not completely sure that I will say a lot of things about birational surface map, but I try to develop at least a general theory in any dimension. Okay? Thank you.
So for general surfaces, is there lambda 1 and lambda 2 in this kind of proof? You did P2, and more generally for surfaces, is there such a statement?
What?
So you defined, so you started with a self-map for P2. Can I take another surface for this statement?
It's the same. Lambda. I didn't define lambda 1 and lambda 2. Lambda 2 is a topological degree, fine. Lambda 1 I didn't define yet, but it's the same statement.
And the same proof then applies to surfaces?
Yeah, except, so here, no, but here I'm using deeply the fact that P2 is homogeneous. Because what I'm saying is that when you perturb, in fact, the contribution of the positive dimensional thing is positive, non-negative. This is not true in general. And so the proof collapses, really collapse, except if you're, of course, if X is rational, then you can play around and come back to P2, draw the argument in P2, and then you have something. But if it's, and of course for surfaces, you know that, well, okay, outside rational map, rational surfaces, I mean, most of the examples, like 99.999% are regular maps. And so then you don't need to have this, right? So, but yeah. Ah. But there is a problem session, no? Like, no, okay.
Maybe you can, no, does it work? Okay. Maybe you can give an example of a map so that when you iterate the degree grow very fast, but there are no periodic points, just by taking a product of a translation.
Yeah. I know why he's asking to do this, because it's also an important example when you try to estimate the entropy. In fact, this is a funny thing, is that the entropy and the growth of periodic points is exactly, well, you're facing exactly the same problems. So the example that Serge was mentioning, it's very simple. So you get x goes to x plus 1, and take anything like a polynomial of degree d in y. So y to the d. Let's say in the affine plane, right? So in the affine plane, there is no periodic points, nothing, because you have a translation in the first factor. So then, okay, I didn't do the details, the computation, but if you compactify in P2, it's not very clever, because what's happening is that, okay, let me do the exercise of what I want. So it's z, x, y goes to z square, x, z plus z square. Let me take square here, and y square. Okay, so z equal to 0 is mapped to, the line infinity is mapped to 0, 0, 1, and 0, 0, 1 is fixed, right? And you have one fixed point, one point matrimacy, which is here. So in fact, you have only one periodic point. But it's a bit absurd to compactify in P2, right? Because your map is a product map. So why not compactify in P1 cross P1? Okay. But then what's happening is that, so you have maybe a projection down to x. If you look at the fiber over x equal to infinity, what you get is y goes to y square. And then in this compactification, the number of periodic points per L is exactly 2 to the L. And here you can compute lambda 1 equal to lambda 2 is equal to 2. Okay, so it's a very, very simple example. which says that in this matter of computing periodic points or computing the entropies, it's exactly the same problem. The choice of compactification seems to be important. The Rigbyman wants to.
So actually, how do you properly define the set of periodic points for a rational map?
Sorry?
How do you define the set of periodic points for a rational map?
The set of points which are periodic and does not hit the indeterminacy locus. I'm looking only.
So it depends on the completion, on the model you choose, right?
Yeah. Well, it has to depend on the model. I mean, they are in one model, so yeah, the number depends on the model.
Okay.
It's a very stupid example, but you have to keep it in mind when you compute these things and trying to prove birational invariances of this objective. Okay, thank you.